Welcome to part one of the Ontario High School video podcast series dealing with solubility product equilibrium. And there'll be three parts to this, so stay tuned. The solubility product constant is represented by K sub SP. It indicates how soluble a solid is in water. So the solubility product of a compound is equal to the product of the concentration of the ions involved, each raised to the power of its stoichiometric coefficient. So, for instance, the KSP of Fe2S3, which is iron 3 sulfide, is the concentration of Fe3 plus squared times the concentration of the sulfide ion cubed. Calcium sulfate, CaSO4, is a nearly insoluble salt with a solubility product constant, KSP, of 2.4 times 10 to the negative fourth. We want to write the chemical equation that represents the solubility equilibrium of calcium sulfate and the KSP expression, or the equilibrium constant expression. So the chemical equation that represents the solubility equilibrium would have CaSO4, solid, double arrow, representing that this is an equilibrium reaction, forming Ca2 plus aqueous plus SO4 2 minus aqueous. Our KSP expression would not include the solid. We do not include solids or pure liquids in an equilibrium constant expression. We include only, in this case, that which is aqueous. So we have the product of the concentration, molar concentration of Ca2 plus times the molar concentration of the sulfate ion. Continuing with our examination of calcium sulfate, we want to calculate the solubility of calcium sulfate in grams of solute per 100 grams of solvent. We're going to assume that the volume occupied by the solute in the solution is negligibly small. So we'll find the molar solubility first using the KSP expression as the base. So we know that 2.4 times 10 to the negative fifth, which is the KSP value, is equal to the product of the calcium 2 plus ion times that of the sulfate ion. We're going to indicate, since those are unknown, the molarities of those. We're going to substitute x for them, so we'll have x times x, which is equal to x squared. When we want to find the value of x, which would be the molar concentration of our calcium 2 plus ion and the molar concentration of our sulfate ion, we just then have to square root the value of KSP. So the square root of 2.4 times 10 to the negative fifth would give us the molarity of our calcium ion and our sulfate ion as 0.00490 moles per liter. We're going to convert from the molar solubility to grams per 100 grams of solvent. Some things that will help us with this are these facts. 1 liter of water is 1,000 milliliters of water, and because the density of water is 1 gram per milliliter, we can express 1,000 milliliters of water as 1,000 grams of water. We're going to use the factor label method to determine the amount in grams of calcium sulfate per 100 grams of water. So we'll take our 0.00490 moles of calcium sulfate over 1,000 grams of water and multiply it times 136 grams of calcium sulfate in 1 mole. We're just converting moles to grams. And then once we do that, that would give us the number of grams that are in 1,000 grams of water. But we want to know how many are in 100 grams of water, so we're simply going to multiply by 100 grams of water. This will cancel the units of water, but it will tell us how many grams of calcium sulfate are in 100 grams of water. And in this case, it is 0.0666 grams of calcium sulfate. So again, simply a reiteration of our solubility in grams of calcium sulfate per 100 grams of water, and we have our value 0.0666 grams of calcium sulfate in every 100 grams of water, and that would be a very common way of expressing solubility. Well, our next type of problem would be to predict whether a precipitation would occur when a solution of calcium chloride is mixed with a solution of potassium sulfate. We know that calcium chloride and potassium sulfate are both very soluble in water, but when we mix these solutions, will calcium and sulfate ion precipitate? That's what we want to know. So does precipitation, which means rather than staying dissolved, it comes out as a solid, occur when 100 milliliters of 0.050 molar CaCl2 is added to 100 milliliters of a 0.20 molar K2SO4. Our first step would be to determine which ions precipitate, and so it's common to write a molecular equation, in this case CaCl2 aqueous plus K2SO4 aqueous yields CaSO4 plus 2KCl. Now we need to use our solubility rules to determine whether CaSO4 or KCl will be a precipitate. And one of the things that we know from our solubility rules is that sulfates are soluble with just about everything, with the exception of calcium, barium, and strontium, and of course silver, lead, and mercury. So calcium sulfate is a precipitate, so we put a solid in the phase there, and then our potassium chloride will be aqueous. Now, when we write a molecular equation that shows ionic compounds dissolved in water, it doesn't reflect the truth of how those compounds exist in water. And so we'll write an ionic equation to show that ionic compounds that are soluble in water separate into their ions when they dissolve. So the ionic equation here would be calcium 2 plus ion, aqueous, plus 2 chloride ions, aqueous, plus 2 potassium ions, aqueous, plus sulfate ion, aqueous, will yield calcium sulfate, solid, plus 2 potassium ions, aqueous, plus 2 chloride ions, aqueous. Once we've written the overall ionic equation, we can then condense this down to the net ionic equation, which is what we really care about, only that which reacts. We identify the ions that react together by what changes form, in this case phase, from one side to the other. Calcium is aqueous on the reactant side, but a solid on the product side, so it's included. The chloride ion and the potassium ions are aqueous on both sides, so they are not included in the net ionic equation. They do not react. They're called spectator ions. And finally, the sulfate ion is aqueous on the reactant side and a solid on the product side. So our net ionic equation is calcium 2 plus ion plus sulfate ion yields calcium sulfate. I know that this is an equilibrium reaction of a solubility type, so I go ahead and insert my double arrows here to indicate that. To determine whether a precipitate will occur, we have to calculate Q, which is known as the reaction quotient. The molarities of each of the ions that react must be recalculated based on the new volume of the solution. So we take the volume in liters of the original solution times the original molarity in moles per liter. When we do that, the liters cancel, and we get the number of moles of the ion. We then divide that by the new volume of the solution, which in this case is 0.2 liters, and it gives us the new molarity of the ion. So for calcium, we get 0.025 moles per liter of calcium 2 plus, and for the sulfate ion, we get 0.1 moles per liter of the sulfate ion. We've doubled the volume of the solution when we mix them together, so we halved the molarities. This should make sense. Now that we have the new molar concentrations, we can go ahead and calculate Q. Q is set up the same way as the solubility product equilibrium expression, except we substitute Q for KSP because we don't know whether this system's at equilibrium or not. So we'll take our new molar concentrations and line them up and multiply them together. And when we do, we get a Q value, a reaction quotient of 0.00250. We take this value of Q and compare it to K, SP, and what we find is 0.00250, the value for Q, is an order of magnitude bigger, in fact 2 orders of magnitude bigger than the KSP value, which is 0.000024. So a precipitate will form If Q is greater than KSP, a precipitate will form. The equilibrium will shift back to the left where the solid is in the expression. And if Q is less than KSP, there is no precipitate. It's greater, so precipitate forms. This is the end of part 1 of the video podcast series having to do with solubility product equilibria. I want to leave you with a quote from the great physicist Richard Feynman. I believe that a scientist looking at non-scientific problems is just as dumb as the next guy. I wish you well. Stay tuned for part 2.